Welcome back to Integral Calculus. In this video, we're going to be looking at trigonometric substitution. The process of trigonometric substitution is a technique that takes an integral that does not appear to have trig in it in any way, shape, or form, and somehow transforms it into an integral involving trigonometric functions. You can see behind me, I have the inverse trigonometric integration formulas. We derived these by first deriving the differentiation rules, following the rule for differentiating an inverse function, and then using anti-differentiation on that in order to turn the derivative formula into an integral formula. But if you take a look at what we have, it follows exactly what I was talking about. We have an integral that does not involve trigonometric functions. And somehow when we perform the integral, we end up with trigonometric functions anyway. So I should be able to find a different path of finding these integration formulas. And that is something I want to look at here. I also want to look at a general trend. The integration formula involving sine had a squared minus u squared in it. The integration formula involving tangent had a squared plus u squared in it, and the integration formula involving secant had u squared minus a squared in it. So, if you are adding, we used tangent. If you are subtracting, and the variable is negative, we used sine. If you are subtracting and the variable is the positive part, we used secant. Those are actually some rules of thumb here. If I set up a right triangle, we know from our basic study of trigonometry, one of the first things you learned about trigonometry is that in a right triangle, the side that is furthest from the right angle is called the hypotenuse. The two sides that are touching the right angle are called the legs. The leg that is touching the angle theta that we care about is called the adjacent leg, and the other one is called the opposite leg. You know that the sine of theta is opposite over hypotenuse. You know that the cosine of theta is adjacent over hypotenuse. You know that the tangent of theta is opposite over adjacent. And you probably never memorized the ratio definition of secant, but secant is the reciprocal of cosine. So that would be hypotenuse over adjacent. We actually don't need cosine here. Well, we might, but we hope not to. And so, when we know the opposite side and the hypotenuse, we care about sine. The opposite side is going to be in the numerator, so it would be easier for us if that was the variable. The hypotenuse is going to be in the denominator. It would be easier for us if that was a constant. And then the remaining side is going to be the square root of a squared minus u squared. Hey, that looks familiar, doesn't it? But we get that the sine of theta is u over a. And we get that the cosine of theta is the square root of a squared minus u squared over a. And that's exactly what we're looking for in trying to do this integration, right? The integral of dx over the square root of a squared minus u squared. Well, setting up this right triangle and rearranging that equation for cosine, the square root of a squared minus u squared is a times the cosine of theta. And I just realized that I have a dx up here, and in the general formula we're supposed to have a du up there. But what is du? Well, if I go up to the other thing that I had here, I have that u is a times sine of theta, just rearranging that equation. And then differentiating, I'll have that du is a times cosine theta times d theta. So I have a cosine theta d theta over a cosine theta. The a's cancel out. The cosine thetas cancel out. I have the integral of d theta, which is in fact just theta. Well, what is theta? Come back up here to how I set it up. If sine of theta is u over a, then theta is the arcsine of u over a. So we can use a trigonometric ratio in order to set this up. We know that we want to deal with sine because I had that a squared minus u squared going on. And as soon as I know I want to deal with sine, I know I want the sine of theta to be u over a. I draw that on a triangle. I use the Pythagorean theorem to figure out what my other side is. I rewrite in terms of cosine to get that other side, because sines and cosines tend to go together nicely. Let's try this again in the secant case. I know that this should turn out to involve an arcsecant. But even if I didn't know that, I see very quickly that I've got that u squared minus a squared thing going on in the expression. So I'm immediately thinking about secants. Secant is hypotenuse over adjacent. It will be a lot easier if the variable is in the numerator. So I'm going to set it up this way, which gives me that secant of theta is u over a. Then using the Pythagorean theorem, I can figure out that this other side is the square root of u squared minus a squared. This other side is the opposite leg. The constant side down here is the adjacent leg, and the trig function that relates opposite and adjacent is the tangent. So tangent of theta is the square root of u squared minus a squared all over a. From there, I want to rearrange things in a couple of different ways. As we saw before, it would be really nice if I could rearrange this and say that u is equal to a times the secant of theta. Because from there I can get that du is a times secant theta times tangent theta times d theta. Then I also want to take this guy down here, and I'll rearrange it and say that the square root of u squared minus a squared is a times the tangent of theta. And look at what happens when I substitute those things in. Du is a times secant theta times tangent theta times d theta. U is a times secant theta, and the square root of u squared minus a squared is a times tangent theta. Some of these a's cancel out. The secant theta cancel out. The tangent theta cancel out. And then what is theta? Well, if u is equal to a times the secant of theta, then that means that secant of theta is u over a, which means that theta itself is the arcsecant of u over a. Although I have to be a little bit careful there, because when I substituted this in before, I did have these absolute value bars going on. And so if I want the absolute value of secant of theta, that means that I want the absolute value of u over a. Which is exactly the arcsecant formula that we are accustomed to. All right. Up next, we have this formula. Again, we know from our previous study that this should be an arctangent. But even if we didn't have that, the new rule that I have introduced is that whenever you have addition, you're going to want to use tangent. And so I want you to think about this from here. Tangent of theta is the opposite over adjacent. And following the same formula we've been working with all day, we're going to want tangent of theta to be equal to u over a. So I want you to determine how you should arrange the right triangle so that tangent of theta is u over a. From there, figure out what the remaining side of the triangle is and use a trigonometric function to represent it. You're going to want that other side of the triangle, and you're going to want your constant side. Those two things together are going to be useful. As a hint, whenever we're dealing with trigonometry, we almost always end up with sines and cosines, or secants and tangents, or cosecants and cotangents. Mixing between those very rarely happens. But once you have that, write it down, use that to substitute into the integral, and see what happens from there. You should be able to end up with the arctangent exactly as we expect. All right. Once you have spent some time on that, once you feel comfortable with it, I'll see you in the next video.